Hello everyone. I'm going to be talking about the Expectation Maximization Algorithm, also known as the EM algorithm. We are given a vector of observed data and a number of Gaussian probability distributions. The goal of the EM algorithm is to find values for the median and covariance for each of the probability distributions. The first step is to pick some initial value for theta called theta 0. As you can see, theta 0 consists of a median and covariance. Then for each iteration t, we perform the expectation step and the maximization step. In the expectation step, calculate the probability that each object belongs to each distribution j. We were given the number of Gaussian classifiers at the start. We can think of this as similar to k-means cluster centers. We want to know the probability of each object being assigned to each classifier. The maximization step gives us the value for theta for the next iteration. The new theta is equal to a value that maximizes the expected likelihood found in the expectation step. The E step and M step are then repeated until the stopping criteria is met. The algorithm works because the probabilities calculated in the expectation step are larger than the probabilities calculated in the previous iteration. This makes sense because the new value for theta maximizes the probability. Again, this is similar to the k-means algorithm, except the EM algorithm uses probabilities with parameters designed to maximize probabilities, rather than measuring distances. Okay, now we're going to look at an example. So first, we'll pick the initial values for theta for each of the two distributions. We'll use -2 as the value for the median of the first distribution, and 3 for the second. We assume the covariance for both distributions is 2. So, theta d1 is -2, 2, and theta d2 is 3, 2, and the probability for each distribution is 0.5. The size of X is 20,000 data points. Assume we have the data point 0 in our vector of observations. Now for the expectation step. We calculate the probability that a data point x sub I will be assigned to a distribution dj. This probability is calculated for each data point in X for each probability distribution. In this example, the probability weight is trivial as it will just divide away. But this would not be the case if the weights were not equal. The second equation shown is the Gaussian density function and is used to calculate the probability. Here, the probabilities for 0 are calculated for d1 and d2. We can see that the probability that data point 0 will belong to distribution 1 is 66%. As a side note, here we can see that if we had more than 2 probability distributions, the probabilities would need to be calculated for each one. Now that the probabilities for all the data points have been calculated, we move on to the maximization step. The goal of the maximization step is to calculate new values for the median for each probability distribution. Notice that the new medians are weighted averages of the data points where the probabilities are used as weights. To save time, the table shows the values of mu1 and mu2 for iterations 0 through 5. From the table, you can see that the algorithm terminates after 5 iterations. The values for the means of both distribution sets didn't change between iteration 4 and 5. The stopping criteria can vary depending on the dataset. Sometimes the stopping threshold will be used. That's when the change between iterations is less than a certain value. A fixed number of iterations can also be used. The EM algorithm has pros and cons. One of the good things about it is it can be used with different distribution types. I showed a Gaussian distribution in the example, but other types work as well. Also, for the EM algorithm to work, the data must be fitted to a model. Fitting data to a model can reveal hidden patterns. On the negative side, the EM algorithm can be slow on large datasets. Probabilities need to be calculated for each data point for all the probability distributions. This can be a lengthy process when the size of the observed data is large. Also, when a probability distribution contains only a few points, the chances of misclassifying data points increases. Here are some sources that I used to make this video. There's a couple YouTube videos that I found helpful, and also I used our textbook. Chapter 9 had a lot of information about this. That's it. Thank you for watching.